Hello, my name is Susan Farrell, and today I would like to make a presentation on a topic from a mathematical analysis tool. This topic will be about an open sets. Let's start with some introductions regarding an open sets. The open sets can be considered as a set where the every point in B contains all the metric space that it and it contains all the points of the metric space that is near to the point P, and it doesn't have it doesn't include the boundary of or limit of its own. That that means and the open set can be considered as a fundamental building blocks for the topology, and it also has a natural description that can be considered as an open interval generalization in the line of the real number. And also, the open set doesn't have any interval at all. The open sets also consists of a complement, which is closed sets. The closed set is known as a set that contains all the boundary, the limit points, and the boundary points of open sets. And it can be defined using the same topological characteristic that is used to describe the open sets. The closed set can also be thought as an extension of a closed interval on the line of a real number. Yeah, line of the real number. For the first definitions of an open set, we let the X D to be the open sets in the metric space, which is considered to be the subset of X of U of X that is consisting of this property. The property states that for any X in U, there's a real number epsilons which is greater than 0, such that the U is also contained any point in a X where the distance epsilon is from where the distance epsilon is from X. And then we let B X epsilon to be the open ball of radius epsilons for any points. And we also let epsilons to be the set of all points within the distance from X. We can consider the set U to be open if and only if that there's an X is greater than 0 such that the open ball is contained in U. In this image that is shown in the slide, this is how the definition was displayed in the image where the of X is contained in the U, which this is an open set. For the second definition, we can say that the S is the subset of R's to the power n, where the subset is open if there's a ball BXR that is centered in X and also contained in S for X is in N. X is in S. Oh my god. The third definition also states that the boundary of a set in metric space is also considered as the set of point S such that for any epsilon is greater than 0, the open ball contains at least one point in S and one point in that is not in S. For the lemma, they stated that the open ball in the metric space can be considered as an open set. And in order to prove that, we can say that if X is in the ball in alpha, then Bx alpha equals to R minus epsilon, where the epsilon is greater than 0. And if Y is in the ball epsilon of X, then the dxy is lesser than epsilon. By using the triangle inequality, we can get the result. By using all the information that we gathered, we get R, which and this shows that the y is in the B, the ball are in alpha for all the y in the ball epsilon in X. That means that B epsilon X is equals to the B R alpha. For the theorem, the theorem of the open set states that we let the X D to be the matrix space, where the X and the D is the whole space and the empty set respectively. And it is required to satisfy these three axioms below. The first axiom states that the both X and D in the matrix space to be open, the union of open subset collection to be open, and the intersection of the finite open subset collection to be open. To prove that, we need to prove A. For the proof, we're going to prove each of the axioms. X is open. X and D can be easily considered as open, since the whole space contains all the balls and there's no points that they will contain. For the second axiom, we let the AI to be A, where I is in the I capital to be the collection of the open sets that is indexed by I capital. The A can be considered as the union of the AI, and the X is in I to be the arbitrary where the X belongs to at least one of the set AI. And since it was stated that the set is open, we can say that it also contains the ball about X in A. But since the X is since X was thought to be in A, just and it was chosen arbitrarily, we can easily this proves that the A satisfies the second axioms, and that means that the union of the open subset collection is open. For the third axioms, we first let the A1 to AN to be the open sets, and we let the A to be the intersections of AI, and just like previous axioms, we let the X in A to be the arbitrary, and then we let X to be in AI, where I is equals to 1 to N, and since AI is known to be open, for each I there exists Ri greater than 0, where such that the BRI is in the set AI. And then we let the R equals to minimum of R1 to Rn. And then we let the ball R in X and the ball A in the ball A in the BRI in BRIX to be in the set AI for all I is equals to 1 to N. And hence BRX is in the set A. But A is equals to BRX is equals to the set A. But since the X is in A was chosen arbitrarily, this satisfy the third axioms, proving that the A to be an open set. Little remarks about this. We can not every the infinite intersections of the open set is open. The example is that we let the AN to be an open interval where I is in to be an open interval of negative 1 over n and 1 over n in R. And then we let AN to be the open sets, but the intersection of AN gets the results in 0. That means that and 0 is not considered to be open. As for lemma, it, it was stated that the set is open if and only if the set is equals to the union of open balls collection. To prove that, we'll be using the theory using was based on the theory a theorem we just proved previously, statement where it states that the union of the open ball collection is considered to be open. Alternatively, if the set A is open, the ball about X exists in the set for every point in S in A, and we let the A to be the union of the ball in about X because every ball is a subset of A, and the union contains every point X in A because X is in the X is in the ball about X. We can use the open sets to solve some of this problem. The first problem states that we need to show the open interval to A equals CD is an open set. For the solution, we let the A equals CD to be an open interval where each A is in A capital. One has C less than A less than D, which proves that C minus A and D minus A to be positive. Then let delta eh, to be the minimum of A minus C and D minus A. If delta is greater than 0, that means that delta is lesser equals to A minus C and D minus A, implying that C is lesser equals to A minus delta, mm, less, less than A plus delta, and less equals to D. Hence, B A delta equals to A minus delta and A plus delta is the subset of A. This indicates that the open interval is open. For the second problem, we'll be letting the U to be the set of R square that is given that by U equals to X, Y in R square, where X is greater than 0 and Y is lesser than 0. For this problem, we need to show that the U is an open set. For the solution, we'll be letting the AB to be in U as the arbitrary element, where A is greater than 0 and B is lesser than 0. And then we let R to be the minimum of A and negative B, where R is equals to 0, and we claim that the B ABR to be e to be equals to set U. And then we let the XY in BABR. And then we use then we calculate going through this, and then we get the result of negative R lesser than X minus A, which is lesser than R, and negative R lesser than Y minus B is lesser than R. We simplify all of this, and then we get the A minus RX. eh, A minus R is lesser than X, and which is lesser than A plus R, and B minus R is lesser than Y and lesser than B plus R. By using the definition of the R that is minimum of A and minus B, we get R lesser equals to A and R lesser equals to negative B. Simplify it to 0 lesser equals to A minus R and B plus R is lesser equals to 0. And then we use all of the provided equations, and we get the result of 0 lesser than X and Y lesser than 0. And therefore, XY is in U, and given that XY is in ABR, that means that BABR is equals to the set U, and therefore U is an open set. That's all for me today. Thank you for listening to my presentation, and see you maybe next time.